Okay, all right. Well, happy Monday. Um, I just have a. We're fast approaching the end of the quarter, and I feel like I'm going to run out of content. Um, but uh, but anyway, let's continue on. So we introduced Gibbs sampling, and we also introduced hierarchical models. And last week, I kind of ran some code that said this is how we could run Gibbs sampling in R to kind of model our values for the hierarchical model. So remember, this is the model that we've set up. Is we're trying to figure out the different parameters, that is each individual batter's batting average. Okay, so the players have their own separate batting averages, and we're saying their sequence of hits and outs are determined in part by their own batting average. Yet all of the batting averages together come from a shared overarching distribution, a beta distribution that kind of determines the different batting averages. And we wanted to do some Bayesian inference to try to figure out what are the parameters of the overarching kind of beta distribution that determines the individual players' batting averages. We also wanted to figure out what those individual batting averages are. That overarching beta distribution that determines the batting averages also has its own parameters, which we say come from another distribution, and that distribution has its parameters alpha and beta, alpha or A omega and B omega, to determine kind of our omega parameter, and the omega parameter is used to determine the parameters of that kind of top level beta distribution. And once you have that determines our individual players' batting averages, and then again we have our data being generated from these individual batting averages. So here's our diagram. Again, our low-level data, which is what we're observing, is just a sequence of zeros and ones, indicating hits and outs, and we have hits and outs for each player S. So I think in our model we have 10 players, and some, you got hits and outs. Those players' individual values have their own batting averages, theta S. So theta S is, some proportion, maybe 0.27, maybe 0.28, maybe 0.25 or something, okay? Those determine the Bernoulli, that's the parameter that goes into the Bernoulli distribution that determines the hits. These values, theta S, come from a beta distribution. The beta distribution has two shape parameters, alpha and beta. In our first example, I think we used 81, 219, but we want to allow for that possibility for, we have some other two numbers that, add up to 300 or something, and so we're going to kind of have this, hyperparameter omega that will say, maybe it's not 81, 219, maybe it's 75, 225, maybe it's 90, 210 or something like that. And that's going to be determined by kind of omega. We kind of set off to the side k is equal to 300. Now again, in your specification, you can make each of these things kind of different parameters. Right now we've arbitrarily selected 300, but somebody else could say, I want different kinds of values. So where does omega itself come from? Omega itself comes from a beta distribution, and right now that beta distribution has shaped parameters A omega and B omega, which right now we have 3 and 7 to kind of indicate, we're even less certain about each of these things. Okay, and so here's kind of our diagram showing all of the relationships that we have here. And last week, what we did is we ran some code in R to kind of illustrate how this works. We said, here's our data, and so Y is going to be kind of this big matrix of zeros and ones, and then we said A omega and B omega are 3 and 7, along with K equal to 300, and then omega is going to get sampled from this. Right now we have just kind of some arbitrary starting value, and then the way we're going to select our different omegas is using the Metropolis algorithm. And then once you have once you select an omega value from using the Metropolis algorithm, we can use Gibbs sampling, because with Gibbs sampling you make it conditional, holding everything else constant, and you sample our values. And so this was how we ran it, kind of manually, and I've posted this code, and I do hope you take the time to review it. But today I thought we could introduce a proper tool, I guess, and there are a handful of different Markov chain Monte Carlo tools. And so this method of kind of writing your own Gibbs sampler, works, but the performance of this kind of R code is perhaps not the best. Okay, so R is relatively simple, a simple language to script in, but as far as getting high performance code that generates millions of values very quickly, it's not the fastest, right? And so there are a few tools out there. One of them is JAGS. Another one that's popular is Stan, and these are tools that generate samples of data using MCMC that allow us to kind of do inference here. Okay, so let's see. So just a little introduction to JAGS. It says JAGS is a program that can perform Gibbs sampling quickly for complex hierarchical models. It stands for just another Gibbs sampler, and JAGS is kind of a clone, more of like a open source clone of something called Bugs. So there used to be another system known as Bugs Bayesian inference using Gibbs sampling, but that's kind of been discontinued, and so you can do JAGS. So if you search for it, if you just type in JAGS, it'll pull up information about football teams. So you can type in JAGS MCMC, and you'll find some information at mcmcjags.sourceforge.io, and there's some information here, and you can go to downloads here. Okay, and so on the downloads, so unfortunately SourceForge has a whole bunch of ads here. You can download the latest version. So I believe the latest version for Windows is 4.3.1, and I think for Mac it's 4.3.2. So you can just kind of, I think SourceForge will try to auto-detect what system you have, and you can just kind of click this, or you can go into the folder for JAGS, and then under 4.x you can get kind of the appropriate one. So if you go to Mac OS, you can get the 4.3.2, which was updated earlier this year, and then under Windows, 4.3.1 is the most recent one. What's this? HTML. Okay, so this is what you'll get. You have to install that, and then once you install that, that it's just kind of this separate standalone program, and I believe JAGS has been coded in C, but let's, yeah, so C++, and basically the way you'll interact with it is you'll write R code, okay, using kind of, we'll load up these packages. There's rjags, and then there's r2jags, and these are packages that allow us to write R code that then when we execute it, it turns it into instructions that get sent to, you have this separate kind of program, JAGS on your machine, that acts a bit of a black box. We send our queries and requests there. JAGS does the computations and the sampling, and then returns those values back to R. So, so the way we will interact with JAGS is using this package R2JAGS. So there's a package rjags, and then there's another package R2JAGS. R2JAGS will load rjags, and in my opinion, R2JAGS gives us kind of the simplest interface for us to write our code that will then get kind of translated into instructions that JAGS will use to do the sampling and then return those values, okay? So all to say, this is just going to be a way for us to speed up our Gibbs sampling performance, and we don't have to worry about kind of constructing the actual, I guess, code that will produce random samples. What we do have to do is we have to specify the model that shows the relationships between the different variables. So yeah, this is what I've written. I wrote, using JAGS does not require us to figure out the conditional distributions of each parameter. And instead, what we do is we describe the hierarchical model using the Bugs language, okay? The Bugs language allows us to kind of state, this parameter, let's say the player's theta comes from a certain distribution, like a beta distribution. And then, and that distribution might have its own parameters. And we specify how the distributions and the parameters are all kind of related. When you look at the code for the Bugs language, it is reminiscent of R, but it is distinct, and you'll definitely want to consult documentation. Now, again, because Bugs has been discontinued, sometimes these the links for the documentation has kind of hopped around from server to server and things like that. So this is kind of the most recent set of instructions or documentation that I could find. But again, if I would not be surprised if in a few years, something changes. Okay, and so it lists off here a whole bunch of different kind of distributions. So we can say, our values come from like a beta distribution, or our data is coming from a binomial or a Bernoulli distribution, and you can kind of see how these things are set up, and we specify the values come from, say, the Bernoulli distribution dBern with some parameter, unknown parameter p, or something like that. So this is how all of these different distributions are set up. Okay. All right, so what we want to do is we want to kind of set up our hierarchical model in the Bugs language. So this, again, is our hierarchical model, and I will show you how for us to set this up, okay? So let me, this is our hierarchical, no, this is regression. That's not the one I want. Okay. So I have already installed JAGS on my machine. All right, well, okay, so before I get into this, just to kind of take a step back, we are doing Bayesian inference, which says the unknown parameters are random variables themselves. And because they're random variables themselves, they have their own distribution. And so, the way it would have worked if we were doing a frequentist approach is we would have just taken, a player's string of data, so maybe 5 hits and 5 outs out of 10 at-bats, and we would have said, okay, this player's batting average is, 5 out of 10 for this data set, and that's our kind of our maximum likelihood estimate. And we said, you know what, that's not the best approach because we know in baseball, hardly anyone will ever have a batting average over, say, 0.33 or 0.35. And so the idea that a player would have a batting average of 0.5 is, frankly, a little ridiculous. And so we said, you know what, we're going to model it and say this player's batting average comes from a beta distribution, and we had a prior, and we have a posterior, and the posterior is going to be some kind of sample of values. In the first couple of weeks when we did this, we used a conjugate prior, and that allowed us to say our posterior distribution also follows a beta distribution and whatnot. Here, we're not going to go for direct inference regarding like what is the beta distribution for the posterior, but we just want to kind of generate samples of values that will say, this is what our distribution looks like, our posterior distribution for this player's unknown theta value. And here we set up a hierarchical model that says not only do we have one player with some unknown batting average, but maybe we have 10 players with some unknown batting average. Okay, so the data that I'm going to load when I specify, we'll set up our data here. So this was just to kind of say here are our players' imaginary batting average, and then this is the data that we have. And so we have, we have 10 different players, and we have, a bunch of kind of hits and outs for our 10 different players, and we can kind of, this is just kind of our data. All right, so our model, as far as setting this up, is going to get written using the Bugs language. Now, when you write the model, it gets saved as a function, okay? So here we're creating a model in R called Bayes.model, and it's written as a function. Now this is a nonsense function, because if you were to try to execute this code in R, it it doesn't return anything. Its last line of code is like, assignment. It's not a real function. This is just a way for us to kind of, the model that we want to actually write is written here, and just kind of, it's almost like just a container to hold the code that we want. It's not a real function. We save it as a function, but it's not a real function. Okay, so this shows the relationship between all of the different things. So here we say each player has their own theta sub s, which is drawn from a beta distribution where the shape parameters are alpha and beta. Okay, and so we're saying, for s in 1 through the number of players, so we got 10 players, and so each player is going to have their own kind of theta value here. And then we're trying to explain our data, and we're going to say, the data is this kind of big matrix. We've got row S for player 1 or player 2 or player S, and then and that player is going to have, say J at bats. And so it's for J in 1 through the number of at bats for player S. So player 1 might have 500 at bats and player 2 might have 520 at bats or something like that. Okay. So, so we're specifying this, and we're saying that outcome, the hit or the out, comes from Bernoulli distribution, and that Bernoulli distribution's parameter theta, is whatever theta is for that particular player, theta S here. Okay, so this is explains how our data in Y is generated. So it's just kind of setting up the relationship between these things. Okay, where did alpha come from and where did beta come from? So remember, so far what we've explained is where the y's come from. The y sub is here. Here I have, I guess, js comes from Bernoulli. The Bernoulli has some parameter theta s. Theta s comes from a beta distribution with shape parameters alpha and beta. Alpha is equal to omega times k minus 2 plus 1. Beta is equal to 1 minus omega times k minus 2 plus 1. All right? So that relationship is shown here. But omega itself comes from a beta distribution. Okay? And so we're going to say omega comes from a beta distribution where the values are a omega and b omega. And so these are the values that we've arbitrarily specified. We said a omega is going to be 3, b omega is going to be 7, and k is going to be 300. So these are kind of these are the ones that we've arbitrarily specified. There's no random component here. So the difference is if there is kind of a direct relationship, we use the assignment operator like R, okay? So we'll say, assign 300 to k, 7 to b omega, 3 to a omega, and then alpha and beta are also kind of determined in this deterministic fashion, whereas omega is a random value sampled from the beta distribution. The outcomes of y are sampled from this Bernoulli distribution, and then the individual players' batting averages theta sub s are also determined randomly from the beta distribution. So basically, the JAGS is going to look for kind of these tilde operators to say these are the relationships where things are being randomly drawn, and we're going to want to generate posterior distributions for each of these things. And the ones, these are values that are assigned, and there's kind of a deterministic relationship. Is that okay, going from our hierarchical diagram or model to how it is being written up inside the Bugs language here? Okay, so I think, so I've basically written it down in here, and I've written a few lines or a few slides kind of trying to explain how this works line by line. So again, when you specify the model in R2JAGS, you wrap it in a function, and again, it's not a function that gets run, but it's just how we store our model. Okay, and then again, inside here, we're looking at our players' values here, which are drawn from this beta distribution, and then for this is trying to explain the actual data matrix in Y, and then the omega values come from a beta distribution, and then these are all kind of determined deterministically here. Okay, so this is how we specify our model. Once we specify our model, we're going to kind of provide a list of values here. And so these are values that do exist already in our global environment. So as part of generating our data, we said we have our data Y, We have the number of at-bats, the number of players, and things like that. And so we are basically just providing a list of names. So these are the names of the different objects in R that represent data. And so these things are values that will not be updated. We are not going to sample these. These are things that are kind of set in stone. So what we're doing is we have the data has come in. This has been collected. The data itself is not subject to randomness. And so we're going to put that into our list of kind of names of data things. These are things that aren't going to be sampled. Okay. We have model parameters. These are the names of the objects that represent model parameters that we do want to sample for. So we do want to figure out what are our theta values, theta representing the batting averages of our different players. This theta is a vector of length 10 because we have 10 players. Each player has their own batting average, and so we are going to want to generate values for each of our 10 players. Okay, so this is the model parameter. Omega is the, again, in our hierarchical model, it's the parameter that's going to determine what are the kind of alpha and beta values that go into our beta distribution here, where the thetas are drawn. So that is also the name of the parameter that we want to do inference for. Okay. So we're specifying the values here, and then what should be some initial values to use for theta and omega. So we have to just kind of start off somewhere. And so, as far as what are some initial values, here we're going to just generate kind of 10 values from a beta distribution, 3,7. So this is our code here, and we're going to say, all right, just generate 10 random values for theta, just generate one random value for omega. And these are just some initial values. Doesn't really matter what numbers you use, but here I just said, just generate some random values here. Okay, and then now we are going to call JAGS and have it execute the thing. And so maybe I'll separate these out. There's a few different lines that need to get run. So we're going to say the data values, or at least the names of the data, come from this list, data underscore JAGS. The initial values come from this list with kind of our model initial values. The parameters that we want to save, parameters to save here, are the names of those things are in this list or vector here. We're going to run 3 chains. We want 15,000 iterations, and we will discard the first 1,000. So that's the number of chains, number of iterations, and then how many values are in our burn-in period. And then the model.file is specified in this function called base.mod. And that is what's going to get run here. Okay, so let's go ahead and run all of this. So I will store our base model here into R. We're going to add just the list of names, data JAGS, our model parameters, and our initial values here. Okay, so this is just to kind of specify it, and then the actual execution here is going to get run when I call JAGS. So here I'm going to kind of just set an arbitrary seed. We're going to make a call to JAGS, And so this, again, is going to send all of our information from R to this kind of black box that's sitting on our computer after we downloaded and installed the JAGS program, okay? So there's a separate executable. R is going to send it down that way. And so this is, it's running and it finished, okay? It says initializing model, and then we saw the little stars go across, and it generated kind of 15,000 values, and it sends everything back, and it gets stored in Bayes model fit. All right, so we've done our kind of Bayesian inference here. All right, I guess before we look at our results, let me give you your first view quiz answer, which is the letter D, D as in dog. Okay, so let's go ahead and take a look at what we got as a result here. Actually, so let me... So here we have our 11 parameters. We have the omega value, and we have our 10 theta values, and it shows us kind of the distribution for each of these things. So again, the contrast here between the frequentist view and the Bayesian approach is that the frequentist, you just get kind of one parameter estimate. Based on your data, you say, my best guess is 5 out of 10, you know, my batting average is 0.5. Here, based on each player, we have a different kind of batting average, and to kind of reflect that it is a distribution, we have kind of different percentiles. So we have the 50th percentile, 25th percentile, 75th percentile, the 2.5th percentile, and the 97.5th percentile. We get the mean of each kind of vector, or mean of each thing, and then we get a standard deviation for each of these things as well. Okay. And so if we wanted to kind of take a look at any of these individually, we can say, you know, we can call plot. And this plot, this is a little bit tougher. A little bit tougher to read, but this, we get kind of a different value for each of our things. So we have one omega thing, and this, there's a little dot here that kind of indicates your center, and this is your kind of 90, I guess, 80, sorry, our median and our 80% confidence intervals, or I guess probability intervals. And so here we have 10 intervals, one for each player. And so we can see, okay, you know, player one's batting average is somewhere around here with an 80% probability interval here. You know, player two is higher, player three is a little bit lower, player four is higher, and so on and so forth. And we have, you know, these different kind of values going on. It's a little bit hard to read, but it's basically little probability intervals for each of these things. You can do a little bit of diagnostics by checking the trace plot. The trace plot shows what were the values being sampled by the Markov chain itself. So this represents, I guess, the deviance here, but here is omega, and what is going on here? This is kind of, it's really hard to see, read or make sense of, but there are three colors, one for each of the different random chains that we ran. So we had, remember in when we made a call to bugs or JAGS, and we said, you know, run it, we said run 3 chains. And so this is plotting all 3 chains, you know, a blue one, a red one, and a green one. And what we're seeing is kind of the random walk nature of the different values that were sampled. And this is kind of what we want to see. This reflects that the values that we're sampling, despite being the Gibbs sampler where everything's kind of a conditional thing and it's a Markov Monte Carlo, Markov chain Monte Carlo, where things are dependent on the previous value. This does look fairly like the values that we're getting are, they look like they're IID. Okay, we don't see this kind of trending kind of pattern or flow that we can kind of trace out. So I don't know if in your homework, if you've already tried looking at some of the MCMC stuff for homework 5 yet, but depending on well, at least maybe in the notes, if you remember, like we had different Markov chains where there was kind of that flat regions, and looked like a skyline or something, to kind of, and that showed that like the values that were being generated were not really IID. Okay, and so here these things look pretty good as far as IID, and that just kind of shows the way JAGS is set up to kind of sample these things. We get pretty decent values. Okay, and here we have chains for each of our theta values, and so there's a whole bunch of these things, and right now I don't see any kind of issues that would be cause for concern. So as far as the diagnostics things regarding the trace plot, we have that. Okay, there's a few other libraries that we could load that can be used for further diagnostics to kind of see how our model has worked here. Okay, so we'll take our Bayes model fit. There's something that we can kind of turn it into an MCMC object, and we can do kind of run something called an XY plot on this, and this will show kind of all of our chains, and again, we don't. This just kind of, I think this shows all 10 of these things. So you have this, and I think this is the same chain. I didn't actually like zoom in myself, but I think this theta 10 is the same as this theta 10 here, but it's hard to really see. Okay, so it just kind of produces all of the plots all at once there, and here is the density plot. Okay. Okay, and so here we get there's three kind of overlapping colors to indicate just the resulting density estimate of our distributions for the different parameters here. So we have, so for player one has his own batting average, theta 1, and theta 1 is centered at around I don't know, 0.26-ish, I think. Yeah, so player one's batting average is the median is 0.258, and that's reflected right here. And this is kind of your estimated distribution, posterior distribution for player one. Going, I guess, 2.5 percentile, I would guess to be around 0.22 or something, just kind of looking at this. Let's see, our 2.5 percentile, yes, 0.225, and our 97.5 percentile is 0.289, so around 0.29, and that's what we see reflected here. Okay. Whereas if we look at, say, player two, we can see this one has been scooted up, right? Has a higher median, so you have to kind of pay attention to the scales here. And so player two, their batting average median is at 0.28, 2.5 percentile is at 0.25, and 97.5 percentiles at 0.315. And that's reflected in this plot, okay? 0.315, 0.25, and around 0.28. So this kind of shows all of the different posterior distributions for each of these parameters here, okay? All right, so that is the JAGS model. Here is just a couple other, another way we could do this, okay? So we specified in our data, we took the individual actual hits and outs, and we said those hits and outs were coming from a Bernoulli distribution, right? So I think this is all I've done here, showing the same kind of plots here. Oh, you can take the bugs output and you can look at the actual values themselves. This is the sampled values, and we saw a plot of just kind of the different values that we saw summarized with a density plot here. Okay. So here, what we're going to do is we're going to model the total number of hits. So this is a second model that I've created in JAGS. Okay, it's very, very similar. Okay, but under this model, we modeled the individual hits as zeros and ones using the Bernoulli distribution. And here, rather than looking at the individual hits, we're going to look at just kind of like the total number of hits out of total at-bats. So this is just this is a very similar model, except rather than looking at a Bernoulli for zeros and ones, we're going to just say how many hits total did they get for this, how many hits did this player get, right? So we have player 1, so this is the number of at-bats, and player 1 had a total of 118. So I could do 118 out of 486, and this is player 1's own kind of individual observed batting average, okay? And so rather than looking at the actual count, so I could take, so this was player 1's actual sequence of outs and hits. You got a whole bunch of outs and, this many hits and whatnot. We're just taking the summary value. So the first JAGS model, we modeled the actual data, the Y's, saying the zeros and ones come from Bernoulli. This time we're going to just look at the summary values and just say player 1 had 486 at-bats and they had 118 hits. And so you could specify, depending on how your data is provided, you can still specify a model here. And so almost everything else is the same, except here we're going to say the Y values, which is just like that number 118 out of 486 hits, is going to come from a binomial distribution. So we're going to use D binom. The rate parameter, probability of success, theta is theta sub s, and that player had so many at-bats, 486 at-bats for player 1. Okay, and so how do we specify this? We have to kind of consult the bugs model specification here, but here we can say, okay, the as far as the binomial goes, we have P and N. Oh, here I wrote D binom. I think it'll still work. Okay, and so I've specified it this way. Theta comes from the beta distributions with shape parameters alpha and beta. And again, alpha and beta are determined by omega. Omega itself comes from a beta distribution. And so this is what our Bayes model looks like. So very, very similar, just ever so slightly different, where over here we're modeling the individual at-bats, zeros and ones. And here we're just looking at the summary total here. Okay, and we'll try looking at this. and we'll let it run, and we can kind of say, all right, what kind of values did we get? And we get very, very similar model outputs, okay, over here. And we can kind of, kind of plot this as well. Ooh, didn't realize my noise. Okay, so this is just kind of the results of specifying our model in a very similar fashion, but just getting slightly different numbers here. Okay. I don't know how we feel about this. Okay. All right, and then I think, and I didn't fully test this last one out. Okay. I don't know if I even talk about this. Okay, so the final JAGS model that I've specified here is, what if we didn't want to specify? So here we just arbitrarily picked k to be equal to 300. So remember, the way our beta distribution is determined is basically we have these two numbers that add up to 300 that are going to kind of determine the center of our beta distribution. So the individual player batting averages come from some beta distribution. When we first started off, we said it comes from beta distribution with shape parameters 81 and 219, but maybe by changing omega, this beta distribution can shift a little bit to, say, 75 and 225, or 100 and 200, or basically any kind of two numbers that add up to 300. But you might say, well, I don't know how I feel about using this number 300. Maybe I want to use the number, have two numbers that add up to, say, 200, or two numbers that add up to, say, 500, to kind of change how much initial confidence we have in our things. And so we can try modeling our k as a random value itself, okay? And so this will be kind of another hyperparameter setup in our hierarchical model. And this would be kind of a pain for us to try to figure out, what is the conditional distribution to set up. And thankfully for us, with JAGS, is we just have to kind of say, like, hey, try this as a random variable, and it will try to generate values accordingly as well. So here, as far as the model specification goes, it's identical to model 2, where we're going to just kind of model the total number of hits. But this time, we're going to say k is not deterministic here as 300, but it's going to come from a random distribution. And here I arbitrarily specified the parameters of this random distribution to be d gamma with shape, with parameters 2, 0.008. And this allows us to kind of pick any kind of values from, say, 0 to, over 1,000, with higher probabilities around, say, 200. Okay? And we can try running this one. Okay, so let me do that, and we'll say run, and so it's running the model here, and now so as far as what k should be, okay, the 50th percentile is around 297, okay, but we're going to get this very kind of skewed distribution regarding what the lower and the higher upper thing. Our mean is 330. does it dramatically affect our thetas? Not dramatically, but we can kind of create a plot here, and so now we can see we now have a value for k itself with a mean right there. I can run a couple more. So these are the trace plots for each of these things. We're going to have a trace plot for k itself. This is, again, tough to read. But as far as the density plots, what we want to see is, all right, so here is the density plot for k with kind of a peak around 300, but we could also see that it is right skewed. And some of our chains, sampled some really high values for what k could be. And this just kind of reflects the the different kind of random parameters that we've set up here. Okay, so again, with Bayesian inference, we're not going just for single value estimates. Now, you might look at this and you go, oh man, we should just stick with the frequentist method and just go with single parameter estimates, because that seems a lot easier. But the extra work here with Bayesian inference is that now you get these distributions for each of these things, and then you can use those distributions themselves as part of your inference. So remember, when you do something like Monte Carlo estimation, you need a bunch of random values to plug into your Monte Carlo estimator, right? So you just kind of take those random values, you plug them in, you take the mean of the thing, and you get this decent estimate for what your expected value is. So we have that. Okay, let me give you your second U-quiz answer, which is the letter E. E as in elephant. Okay, I've got one more example here. And here we're going to do say regression, okay? So here I'm just generating some random x1, x2 values. Okay. And we have a regression model, and but we also have some random error here, okay? So x1 is normally distributed. x2 is kind of this this binomial or Bernoulli thing, either zeros or ones, okay? And I don't know what the answer is going to be here. The true answer, okay, we're going to say y is determined by, we have intercept 1.5, and then we have slope 1.2 for beta 1, and slope negative 3.1 for beta 2, but we also have some random error. So this is going to be our true relationship between the variables x1, x2, and y. Okay, so we have a slope of 1.2 for x1, a slope of negative 3.1 for x2, and then we have intercept 1.5 and random noise e. That's going to be our true relationship. Okay, and so I'm going to kind of put all of our thing together into a data frame, and this will be our kind of our simulated data, and we just have this is our y, our x1, and our x2. And the frequentist model, we would just do something like this. We would say LM, what is the relationship between y, x1 and x2, using this, and then we could say, all right, give me your estimates. And it gives us, decent estimates based on the values that we have. We say, all right, its guess for the intercept is 1.849. Its estimate for the slope for x1, which is 1.135, the true value being 1.2, and then its estimate for b2 is negative 3.09, where the true value is negative 3.1. So it does a decent job of estimating these things. And this is LM. This is the LM that we've learned to kind of love and trust, and it does kind of its best that we have there. Okay. And again, the Bayesian approach just says, hey, you know what? I don't love that we just have one number here. I want to try to model this as a random variable itself, right? That our slope values isn't just some determined number here, but it should be modeled using a distribution. Okay, I understand there's a tiny bit of irony here because under the true model I have used deterministic values. Okay, but we could also specify as some kind of random thing. All right, so how would I set this up using the Bayes model? Well, here we're going to say there is a true kind of mean value. Okay, the mean value is determined by an intercept plus some unknown beta 1 times our x1 value plus some unknown beta 2 times our x2 value. Okay, and these are the parameters that we want to estimate. The intercept, our beta 1, and our beta 2, and we're going to say these are the parameters that we want to estimate here, and these are going to go into our Bayes model parameters. Okay, and that's going to kind of determine the mean of our linear regression line. Okay, but the actual values themselves, the y that appears in our data is, comes from a normal distribution where the mean is mu1 and there's some kind of random error. Okay, some random error tau here. Okay, and so here we kind of have some what do you call it? Prior distributions for each of these things. Now, a little bit unfortunate is these values for the normal distribution in the Bugs language is that they are, I think they use precision rather than, they use a tau, which is kind of a 1 over variance, which feels weird. Okay, so we're accustomed always to like x minus mu squared divided by sigma squared. Okay, but here the tau appears in the numerator, and it's tau is basically 1 over sigma squared. Okay, so it's a weird thing. It's a weird thing. It's they call it a precision thing. So that's just something to keep in mind. So so here my prior distribution, I picked some really wild prior distributions, very kind of wide things. So here I have alpha basically centered at 0 with a standard deviation or a variance of 100, basically a standard deviation of 10. So alpha could be, anything from like negative 20 to plus 20. I mean, technically anything from minus infinity to plus infinity, but 95% between negative 20 and plus 20. And then for our slope parameters for beta 1 and beta 2, I picked uniform distributions going from negative 100 to 100. Okay, the true values are what, 1.2 and negative 3.1, and I just picked some really wide values there. And then as far as the tau parameter, as far as what is the precision the inverse of our variance, I've got d gamma here, okay? So just a gamma distribution, 0.01, 0.01, I think gives me just this kind of really wide shape here. So this is going to be how we're going to specify our model, and we'll do some inference here, okay? I'm going to pull out each of these things, our y, our x1, our x2, and our n, and this is going to go into our list of names for the data that goes into JAGS. The parameters that we want estimates for will be alpha, beta 1, beta 2. We need some initial values just to kind of start off our chain. And then I'm going to say run 3 chains, 9,000 iterations, 1,000 in our kind of burn-in period that we'll just end up throwing away. All right, so I go ahead and I run this. And then let's kind of take a look at what it outputs. Okay, so now its estimates after kind of running Bayesian inference. Let me compare this to our frequentist model. Our frequentist model, our intercept was estimated at 1.849, 1.13, and negative 3.09. And we get, very similar values for the 50th percentile, or even our mean here for alpha and what beta 1 and beta 2 are, but we also get basically a distribution for each of these things. Okay, 2.5 percentile could be for alpha could be as low as 1.271, 97th percentile is as high as 2.435, and we get kind of a lower and upper bounds for what our slope and our intercepts, what our slopes can be for each of these things. Okay, where the 50th percentile is right around negative 3.1, which aligns with our frequentist estimates. The frequentist estimate was negative 3.09, and we get that for the mean here, and 50th percentile is right around there. But we also get values for 95th, 97.5th percentile for what those things could be as well. Here's our trace plots showing each of these, what are different estimates for alpha and beta R. And then let me also just kind of copy this. Shape estimates for what our intercept and our two slope values are. So centered around 3.1 again, showing kind of the results of our different traces here. So anyway, this is doing kind of Bayesian inference where you're going to get posterior distributions for what each of these different kind of parameters can be, and then you could then take those sampled values and throw them into, say, some kind of Monte Carlo estimator if somebody were to ask you a question about, what is the expected value of, some kind of future prediction, right? For, if X1 is, 5 and X2 is 1, what do you predict? And you can kind of plug in, rather than just saying, this is the one value. Okay, so if I said, X1 is 5 and X2 is 1, you would plug those values in. Under the frequentist model, you would just kind of plug in, the slope and the intercept, and you say, we expect this. But here we can actually say, all right, this is what we expect, but here's a probability distribution on that. Okay, that's it for today. Just showing you a demonstration with JAGS on how to do a little bit of different, I guess just a quick introduction to some Bayesian inference here. Okay, last view quiz answer today is the letter C. C as in cat. C as in cat. And we'll wrap it up here. Have a great rest of your day. Thanks for coming.